So here we have what's called Taylor's theorem or Taylor's formula. Some people even call it Taylor's inequality. This is reminiscent to the alternating series estimation theorem that we've seen in the previous two videos. But this is called the Taylor's theorem, because it represents the remainder for a Taylor series. And again, the remainder term is simply the difference between the actual function minus the Taylor polynomial approximation. Now, just keep in mind, this is similar to the estimation theorem, right? Where we have R of n being equal to the difference between the actual sum of the series, of the alternating series, minus the partial sum of the alternating series. So this is going back to the alternating series estimation theorem. But now we're applying this to a series that is not necessarily an alternating series. So Taylor's theorem takes this idea that we saw in the alternating series estimation theorem, and it just generalizes it. So we have the remainder, which is again an error term, a remainder term, which is simply the difference between the actual function minus the Taylor polynomial, which is the approximation to the function. So that difference is this remainder theorem. And according to Taylor, the Taylor theorem, the remainder term is equal to this expression, which also is reminiscent to the alternating series estimation theorem. We take if you want to find the remainder term given by the difference with the nth degree Taylor polynomial approximation, then we take the n+1 derivative of the function evaluated at z. We'll talk more about what z is compared to a into x over n+1 factorial. So this looks like the coefficient of the Taylor series, x minus a when you have a Taylor polynomial centered at a particular value a, to the n+1 to the exponent of n+1. So for now, just consider this as my formula for the remainder found. Okay, so now let's look at an example where I want to find the Taylor polynomial with degree 2 centered around or at the value of a equals 4. That's what this tells me here. N is going to tell me the degree of the polynomial. And I want to know what is we're going to use the interval soon when we find the remainder term. For now, I just want to find the Taylor polynomial with degree 2. So again, just to recall, what is the Taylor series? The Taylor series is some, right? Some sum of power functions written as x minus a, where a is the center of my polynomial or series. And I have some coefficients, and these coefficients look like the following. These coefficients look like the nth derivative evaluated at a all over n factorial. So this is the Taylor series in all its glory, right? And this is called, the Taylor series. Now the Taylor polynomial is just a truncation. It's a portion of the Taylor series. And it tells me specifically what degree I want. So I wanted a Taylor polynomial of degree 2. So if I want a Taylor polynomial of degree 2, we call that T sub 2 of x, which just means instead of taking the sum of this, I just stop where n equals 2. So I'm going to take the summation, go from 0, and just stop at 2. And then this would be same thing again. Sorry for that. Should be nth derivative at a over n factorial x minus, and my a value here is 4, so I'm going to replace that with 4 instead to the nth power. And so if I draw this out a little bit more, I would get, when I plug in 0, I get f of 4 over 0 factorial plus f prime of 4 over 1 factorial x minus 4 to the first power plus f double prime of 4 over 2 factorial x minus 4 squared. So this is the drawn out series. This is part of the series where we stop at the degree being 2. And this represents the Taylor polynomial of my function. So the first order of business is to identify what is the value of the function at 4. Well, it's just the square root of 4, which is 2. So I can replace that with 2 plus, and then f prime. What is f prime? Well, f prime of the derivative of the square root function is 1 over 2 rad 4, which is a fourth. So I have this as a fourth x minus 4. And then I'm going to add plus. So now I look at the derivative of derivative, which is f double prime at 4. And just to make sure we have no issues with this, I'm going to just move this a bit further down. So if we have f of x is x to the 1/2 power, so f prime of x is 1/2 x to the negative 1/2. And so then f double prime of x is equal to negative 1/4 x to the negative 3/2. So this is going to be negative 1/4 times 4 to the negative 3/2, which is the same thing saying negative 1 over 4 times 4 to the 3/2, which is negative 1 over 4 times the square root of 4, which is 2 cubed, which is negative 1 over 4 times 8, which is negative 1 over 32. So this is going to be negative 1 over 32 times 2, which is 64. And this is x minus 4 squared. And so this is the Taylor polynomial of degree 2. So finding the Taylor polynomial is straightforward once you know how to find the Taylor series. Taylor series requires an infinite number of terms. Taylor polynomial takes just a finite number of that infinite number of terms. So I found it. Now, just to give us a bit more understanding of what we actually are doing, I want to show you on Desmos what I mean by a Taylor polynomial approximation. So I've graphed the function square root of x. Now I'm going to call a new polynomial t sub 2 of x. And I'm going to actually write out the Taylor polynomial that we just discovered. So 1/4 x minus 4, and it's going to be minus 1 over 64 x minus 4 squared. Now, do you see what's happening? The polynomial that we have, the black graph, is representing the second degree Taylor polynomial of the function centered around the x value being equal to 4. So you start to see that the black graph touches the red graph, which is f of x, precisely at the point x equals 4, y equals 2. And so then this is a pretty darn good, the black polynomial graph is a pretty darn good approximation to the actual graph, the red one that we're considering, for values very close to 4. If you're out here at 1, you start to see that there's quite the divide separation. And clearly, if you go farther out to the right, 15 or even 20, the polynomial approximation, the second degree polynomial approximation to the function at 20 is too far away from the actual value of the function at 20. So values beyond, I would say beyond values of 7 or even 6, anything beyond that, the Taylor approximation isn't that great. So that's why we would extend it and create more and have more terms of the polynomial to better approximate our graph. So that's what we're considering. Now, what we want to do is establish an error bound. How bad, how precise, or how accurate is our Taylor polynomial compared to the actual function? And we want a numerical value for that. So that's why we use Taylor's theorem. So now we have the formula for it. So I want to figure out, using Taylor's formula, I want to figure out the accuracy. How accurate is it compared to the actual function, or how bad can it get? So one way is using the Taylor's theorem. So since we used f of x and we approximated it with the second degree polynomial, then my n value here is 2. So according to Taylor's theorem, my error bound, or my remainder term, r sub 2 of x is equal to the third derivative evaluated at z over n plus 1 factorial, which in this case would be 3 factorial, x minus 4 because a is 4 to the third power. And so what I want to do is I want to make this bound as, I want to see what is the upper bound to this. How bad can it get, right? So first, let's figure out what's the third degree polynomial. And since we know the second degree polynomial is negative 1/4 x to the negative 3/2, then the third derivative is positive. It's positive 3/8 x to the negative 5/2. Or in other words, 3/8 x to the 5/2. Now, what is the z business? So z is the value in the interval that we're given. So what's the interval we're given here? We're given that the x values are between 4 and 4.2. So I want to see how bad or how big I can make this. So first, just take a look at the third derivative. And I want to see how, I want to choose a z value that's in this interval. So z is also within this interval. So z is in the interval for 4.2. So that I can make this as big as possible. Well, to make this as big as possible, I must make the denominator as small as possible. If these are the only two values that if I'm in between these two values, then the smallest I can be is a 4 for z. So this will be 3/8 times 4 to the 5/2, which is 3/8 times the square root of 4 is 2. 2 to the 5th is 32. So this is my value that I get. So this here can be it could be no more than 3/8 times 32, and we'll take care of the computations a bit later. 3 factorial is 6. Now, how big can this be? Well, it can be as big as whatever the x value here would be, and x values range also from 4 to 4.2. So the most this can be would be if the x value is 4.2 in this case, right? I want to make my error bound as big as possible. So I can see what's the worst scenario. That's basically what we're trying to look for. What's the worst case scenario that my remainder can be if I'm in this range, if I were to be in this range. So this would be 0.2 cubed. So when I put this all into my calculator, I'll then see what is the worst case scenario. So let me just show you that. So then when I put it in my calculator, I have quite a number of fractions within fractions. So I can do that. So this is 3 over 32 times 8. I have 6 on the bottom. And I'm multiplying that by 0.2. And I'm raising it to the third power. So this is 0.5. Sorry. Yeah, you can write that as decimal 0.000015625. So let me just bring up my other screen. So what we're saying here is that the remainder Taylor's theorem says that the error bound is at most, or be no more than 0.000015625 of a difference. So what is this saying? This is saying that this Taylor approximation, T2 of x, approximates f of x pretty well for the first 4 decimal places. So it's approximately, so T sub 2 of x, which is the Taylor polynomial degree 2, is approximately f of x. It's quite accurate for the first 4 decimal places. So it's precise. The accuracy is precise within the first 4 decimal places. And that's one way to consider how to do this.